Hi, I'm Mr. Manley, and this is a video on word problems with linear systems. A system, when we say system, we mean a set of two or more equations. And in these problems, we're going to be dealing with two equations. And linear systems means that the equations that we are working with are going to be of the form ax plus by equals c, or y equals mx plus b. These are the typical forms of linear equations that students in algebra and pre-calculus are working with. I'm going to look at 4 or 5 word problems here. Taking the first one, we've got this hockey game where a vendor sold a combined total of 156 sodas and hot dogs. So right there, when I see sodas and hot dogs, and hot dogs, I'm wondering if those are my variables. Because remember, when we look at these, when we're talking about a linear system and we have a linear equation, we're going to want two variables. We're going to want an x and a y. But of course, we don't have to use x and y. We can use whatever variables are convenient or relevant to the context of the problem that we're working on. The number of sodas sold was 2 times the number of hot dogs. So now I'm feeling more confident. There's sodas and hot dogs again. The number of sodas was 2 times the number of hot dogs sold. Find the number of sodas and the number of hot dogs sold. So these are my two equations, or these are my two variables, and I see 2 sentences that are going to give me my 2 equations. So the first equation is pretty obvious, I think, right? A vendor sold a combined total of 156 sodas and hot dogs. So that's S plus H is equal to 156 is the equation we get out of that statement. And then the second one, students might have a little bit more trouble with. The number of sodas sold was 2 times the number of hot dogs sold. The way that I like to do this is to say I'm going to set sodas equal to hot dogs. Now I know that the number of sodas sold is not equal to the number of hot dogs, so how do I need to operate upon this equation to make it equivalent? The number of sodas sold was 2 times the number of hot dogs. So if I have 2 times as many of these as hot dogs, we could think about it and just give ourselves numbers and say, well, if there were 50 hot dogs sold, that means that there were 100 sodas because there's 2 times as many sodas sold as hot dogs. So with that numeric relationship, or that numeric sort of guess example used, I can see that the 2, if I put the 2 there, that will make those equations equivalent. And now I've got my system of 2 equations. This is something to keep in mind and carry forward, that if I ever have a system of equations in 2 variables, I will be able to solve the system if I have 2 equations. And moving forward, what you'll see is that if I have a system of equations, and I'm saying linear system, if I have a linear system of equations, and I have 3 variables, I will be able to solve it if I have 3 equations. So let's go ahead and continue here. How do I solve a system of equations? One way is by elimination, but another way is by substitution. And here we can see that I'm ready to make the substitution, right? I know that S is equal to 2H, so I can substitute for S here. And putting these 2 equations together with that substitution, and I'll say here that I am substituting for S. So I can say 2H plus H is equal to 156. And then we've got a really basic algebraic equation that we can solve here. And I get that H is 52. Then what we do is once we solve for one variable, we back substitute. So that's an abbreviation for back substitute, which means we use the value that we have in either of the previous equations to find the other variable. So it looks really simplest to plug it into the second equation. S is equal to 2 times 52, and I get that there were 104 sodas sold. So find the number of sodas and the number of hot dogs sold, and I've got it there. That's 104 sodas and 52 hot dogs. Okay, so there's one. Let's take a look at another one here. A party company has chairs and tables for rent. The total cost to rent 3 chairs and 2 tables. So again, I'm identifying my variables, chairs and tables. And the total cost to rent 12 chairs and 2 tables is chairs and tables, $47. And just a side note, I really dislike these problems because they're masquerading as real-life applications of the concept of solving a linear system and really trying to make us believe or represent this as, oh, this is something that you could use. This is something that you could have to do, which obviously it's not. So I don't like that. But it is a canvas on which to practice solving of systems and to reinforce the idea of systems of equations to solve for unknowns, although they are really terrible examples. Okay, so moving forward, taking the first sentence, I can do 3c plus 5t is equal to 50, and the second sentence gives me 12c plus 2t is equal to 47. I have the system of equations, and as I mentioned in the previous problem, we have a couple of ways of solving a system of equations. We can either solve by substitution, or we can solve by elimination. This one I'm going to solve by elimination. You recall the last one we solved by substitution. Solving by elimination, I need to get one of the coefficients on the variables to match up by multiplying the equation by some real number value. So if I multiply the first equation by 4, I'm not going to have to do anything with the second equation, because look what's going to happen. The first equation is now going to be 12c plus 20t is equal to 200. This 4 gets distributed to every term on both sides of the equations. Be sure to do that. I even forget to do that. Sometimes, once every 30 or 40 times, I forget to multiply the other side. So I would forget to do 4 times 50 and just carry down the 50. So just stop and check yourself and make sure you don't make that error. And then the second equation stays the same because I have a 12c already. And then we're going to just subtract these. And again, what I like to do actually is when I say subtract, I put parentheses around the second equation. And that reminds me that I have to distribute the subtraction. I have to subtract everything. It makes sure that I don't just subtract the 12c. So 12c, let me just show you. An error that students will make is they'll just put the minus sign and they'll go 12c minus 12c is 0c. And then they'll go 20 plus 22. And they'll forget to subtract the 2t. They'll just focus on subtracting the 12c. To prevent myself from doing that, what I like to do, as I said, is put parentheses. So parentheses there. And then I go 12c minus 12c is 0. 20 minus 2 is 18, t. And 200 minus 47, what is that? That's 153, I believe. And then I can solve for t. 18. I bet 18 is a factor of 153, but I'm going to have to take it in steps here. These are both divisible by 3, so that goes 6, and that goes 51. That's interesting. 51 over 6, and that is not divisible by 6. 3 goes into this 17 times, and 3 goes into this 2 times. So 17 over 2. What is the cost to rent each chair and each table? So, I mean, I guess we could have a, it doesn't have to be a nice, neat whole number when we're solving these. So according to this, remember we are in this line, we are solving for tables. According to this, it is $8.50 to rent a table. $8.50 for a table. Certainly possible, but I'm going to check my work at the end to make sure of that. Now we go to the back substituting step, like we had in the previous problem. So we're going to back substitute. And we have the t, right? So I'm going to substitute the 8.5t in either equation above. So I'll do it in this first equation, plus 5 times 8.5 equals 50. Let's see how far I can get without a calculator here. Let's see, 3c plus, all right, 5 times 8.5 is 40, plus 2.5, so that's 42.5. Okay. And 50. Then I'm going to subtract the 42.5 from both sides. So 50 minus 42.5 is going to leave me 7.5. Okay, that number looks like it's going to be convenient, I think. 42.5, and that's 7.5, and then we divide by 3. And 7.5 will be divisible by 3, right? That's going to be 2, carry the 1.5, looks like 2.5. So that would be $2.5 or $2.50 for the chair. Fair enough. Those are, and I mean, that's fairly convenient, right? But we could come out with anything. I mean, if I came out with $2.37, certainly no reason that can't be the case. But I do want to go ahead and check this. So I'm going to go over here down in the bottom left. And I'm just going to plug these in. I'm going to plug them into the second equation and check there, since I was working with the first equation in the back substitution. So I'm going to 12 times 2.5 plus 2 times 8.5, and expect that that's going to equal 47. So 12 times 2.5 is 24, plus 6 is 30, plus 2 times 8.5 is 16, 17, which is 47. And that one does check. Okay, very good. I think I'm going to, we're up on 15 minutes here, and I'm probably just going to do one more because I don't want to extend this too long, and you're getting the idea. You're trying to read the equation, set up a system, and then solve the system. And yeah, there are going to be some different types of systems to set up, and that's part of the problem solving of mathematics, right? You have your basic skill, you have your fundamental approach, and then you want to be able to apply that on your own to different situations. So let's see what I want to look at here. I guess this one would be as good as any. A family has 2 cars. During one particular week, the first car consumed 25 gallons of gas, and the second consumed 20 gallons of gas. So I think what I'm getting here is my first car, which I'll call A, and my second car, which I'll call B. Might be wrong about that, but yeah, I think that's probably going to be what my variables are. The 2 cars drove a combined 1,375 miles. So I'm going to have a car A and a car B. How far did car A drive? How far did car B drive? And the sum of their fuel efficiencies was 60 miles per gallon. The sum of their fuel efficiencies was 60 miles per gallon. What were the fuel efficiencies of the cars that week? So what's fuel efficiency? That's a kind of tricky little direction to go in. Fuel efficiency. And I just wonder if that's maybe a little bit too much to expect that, oh, everybody knows what fuel efficiency is. I mean, I think probably they do. Almost everybody does. But still, if you don't watch commercials or drive a car, or if you take the bus everywhere, maybe you don't know what that is. So fuel efficiency, I'm thinking they're saying, what are the miles, how many miles per gallon? So that's miles per gallon, also known as MPG, right? And that's what my A and B are up here. The miles per gallon for A and the miles per gallon for B. So let's see if we can do the miles per gallon for A and the miles per gallon for B and get 2 equations here. I think the first equation here, if the 2 cars drove 1,375 miles, we're going to do the 25 gallons timed A miles per gallon is how far the first car went, plus 20 miles per gallon, or 20 gallons times the miles per gallon for B is how far car B went, and it went a total of 1,375 miles. So that's a pretty tricky one there, because in the previous problem, or the previous problems, the conversion was right there in the sentence. We just had to convert the sentence to the sentence that was given into a variable. In this one, we have to think about how to combine 2 different sentences in order to get the equation that will help us out here. And the key to it was really identifying what I mean by A and B. What about A? What about car B am I talking about here? And I had to identify that what I'm talking about, what B is actually talking about, is the fuel efficiency, the miles per gallon that B can go. And then the second equation was this, the sum of their fuel efficiencies is 60 miles per gallon. And there we just have a single sentence giving us A plus B is equal to 60. And there I've got my system of equations. So that's a good one to finish on, because it's not just a straight shot from point A to point B, if you will. I really had to think a little bit and think about how I was going to combine the information that was given. And that's good for you. You want to have to think a little bit in order to solve a problem. That's really what mathematics is about, not simply following steps and memorizing steps to follow, but combining information in ways that you haven't combined the information before in order to get a result. So we'll leave that as my lecture for solving word problems with linear systems, and hopefully you will use the basic fundamentals to be able to solve other problems in linear systems.